Right. Hi, everyone. Welcome to the 9th online Spintronics seminar. This is Xin Fan from University of Denver. I hope you and your family are all healthy. Today's seminar is a little bit special in that we're actually trying a live broadcasting of this seminar on Twitch. This is mainly to accommodate some of the audiences with poor internet connection or have restrictions of using Zoom. So this is a trial at this moment and does not affect any operations here in Zoom. So it's my pleasure to introduce our speaker today. Professor Luqiao obtained his PhD from Cornell University in 2012. He then worked as a research staff member at IBM at Yorktown. In 2015, he joined the faculty of MIT in the ECE department and is now an associate professor. He's a recipient of many prestigious awards, including the NSF Career Award, Air Force Young Investigator Award, Macmillan Condensed Matter Physics Award, and the IUPAP Young Scientist Award. His current research interests include spintronics with ferromagnetic and antiferromagnetic materials and 2D materials, as well as inducing magnetic dynamics with topological materials. He's done very well in the past years with a lot of very interesting publications in different areas. So I guess we will invite him back sometime later to talk about his science paper on the interaction between spin waves and domain walls. So without further ado, please, Luqiao, go ahead with your talk.
Many thanks, Xin, for the nice introduction. Thank you all for attending this seminar. It's a great honor to speak here on this online seminar series. I would like to thank the organizer, Xin and Kirill, for making this possible. So today my topic is to discuss antiferromagnetic insulator and platinum bilayer structure. Particularly, I will talk about how we can determine the nature and magnitude of the current-induced effect in such a system. So first of all, I think antiferromagnetic spintronics is already a quite popular topic, and we have already listened to, heard many aspects of this story. And particularly, I think a few weeks ago, Professor Matis Klawi have already given a very comprehensive educational seminar in the same online seminar series. So I think today I will try to avoid duplicating his efforts, and I will only try to give a very brief introduction. I would recommend, if you did not hear that day's talk, Professor Klawi's talk, please go online and watch the video. I think it's very inspiring talk. So let me just briefly mention that I think we acknowledge that antiferromagnet might have some very unique features that can perform better compared with ferromagnet. Particularly, we can get potentially high storage density because there is no dipolar field due to the cancellation of spin sublattices. And then you can put neighboring bead very close to each other. And also, we know there is a very high intrinsic frequency associated with antiferromagnet magnetic resonance. The reason is there is this large effective exchange field, which greatly boosts the precession frequency of antiferromagnet. And then you can potentially get very high operation speed. Despite of those promising prospects, I think it's also well recognized that there are some intrinsic difficulties in realizing useful spintronic device out of antiferromagnet. The reason is, first of all, it's still not very clear whether you can get a very reliable, very efficient way to control the orientation of new vector inside antiferromagnet. Because just use magnetic field as example, the effect on two sublattices largely cancel each other. There is very small magnetic susceptibility. And also, it's very difficult to realize efficient magnetic reading because we know, well, whether we are still not fully sure of whether there is a strong TMR, GMR, or AMR effect associated with AFM, antiferromagnet, just similar to ferromagnet. So all of those studies are still in a very early stage. So I think a very important breakthrough happened a few years ago in Professor Youngworth's group. where I think they did this very important experiment, shows this unique opportunity that inside antiferromagnet, you can still utilize current to realize efficient magnetic switching. This is realized through this mechanism called as Néel spin orbit torque. Specifically, you need a material which has some unique symmetry. And they show that in this semiconductor copper manganese arsenide, because of the local symmetry breaking as those two sublattice location, so for the manganese atom as those two sublattices, they say different local environment, and there is local inversion symmetry breaking. And then that gave the possibility to realize this kind of staggered field-like torque caused by spin-orbit interaction. And then utilizing this spin-orbit torque, they realize switching of new vector along two orthogonal directions. I think this is a groundbreaking work, which basically provides hope of realizing useful spintronic device out of antiferromagnet. Following this work, I think people have also realized the similar effect in other systems. Manganese 2 gold is another system which has this kind of spatial symmetry. And then more recently, people start to utilize magnetic insulator. And here for magnetic insulator like nickel oxide, the hope is to utilize interfacial spin-orbit torque at the platinum magnetic insulator interface, and then use this spin-orbit torque to realize new vector switching. So besides this kind of electrical measurement, I think this kind of current-induced magnetic switching have also been verified using magnetic imaging technique, particularly using X-ray technique like XMLD and PIM. People show that you can switch the domains inside antiferromagnet, like copper manganese arsenide, like manganese 2 gold. I think 2 weeks ago, Professor Clavi also showed that you can get very clean, very high contrast magnetic imaging inside nickel oxide. So basically, the current-induced magnetic domain switching have been very well established using this kind of magnetic imaging technique. So after the verification of the existence of this kind of magnetic switching, the next question is naturally, how can you quantify its magnitude? The reason is only when you can quantify the magnitude of current-induced torque or the current-induced effect, you can start to optimize the effect. You can start to look for a better material or better device geometry in order to fully utilize the effect. But so far, I think electrically quantify the current-induced torque or current-induced effect in antiferromagnet is still quite challenging. The reason is in ferromagnet, we know it's relatively easy to quantify the current-induced effect by simply comparing with field-induced phenomena. Just give you a simple example. If you talk about MTJ, and we know we can use either current or field to cause switching between the parallel and antiparallel states. And then on the left side, you can see that you use the field to realize this kind of minor loop. And then on the right side, you can use current to induce this switching. If you want to know whether the current-induced switching is 100% or not, you can just simply compare the delta R in those two cases. If they are close to each other, you say, hey, all of the magnetic moment are completely switched by current. If you only get about 50% delta R in the current-induced case, then you know, okay, there are only half of the domains are switched, the other half is not. So it's quite straightforward to use field as a calibration standard to check out how the current switch magnetic domains in ferromagnetic system. But in antiferromagnet, it's much more difficult. The obvious reason is there is very small field effect. As I mentioned earlier, because the magnetic susceptibility is usually tiny, so you need to apply a giant magnetic field in order to cause spin flop. Usually this magnetic field is at least a few Tesla and sometimes tens of Tesla. So for example, this figure gives you the result from a nickel oxide thin film. And you can see that you need about 10 Tesla in order to get this sinusoidal behavior. But even up to 15 Tesla, you are still not quite sure whether this is already saturated, whether it's already a field aligned single domain, or whether there is still multi-domains exist in this structure. So this give us big difficulties in comparing current-induced effect with field-induced effect. Okay, so basically, my today's main task is try to, first of all, establish a material platform that can potentially allow us to more easily manipulate magnetic moment or magnetic ordering inside the AFM with magnetic field. And then with this newly developed material platform, we can start to correlate the current-induced switching with magnetic ordering change using field as calibration method. And finally, I will show you how we can, in this system at least, we can calibrate current-induced effect with field, with magnetic field. So first of all, let me introduce this new old material system, which is alpha iron oxide hematite. So the reason I say it's old system because iron is probably one of the richest elements in the earth. So as you can imagine, oxide or iron is nothing new. It has been studied for centuries. And it's well known through the previous study that there are two antiferromagnetic phases inside this alpha iron oxide. And then the first phase is basically this z-axis phase, so where the spins are aligned along the c-axis, the vertical direction, which is the c-axis of a hexagonal structure. And then there is also this easy plane phase, where the magnetic moment in equilibrium lies in the c-plane of the hexagonal structure. In order to toggle between those two phases, the easiest way is to change the temperature. So it's known that there is a transition temperature known as Moriya transition at about 260 Kelvin for a bulk sample. And then below this transition temperature, you get the easy axis phase, and above this transition temperature, you get easy plane phase. So I think there are, well, this is an old system, but recently there are renewed interest in this material. I think well-known example, again, comes from Professor Kawai's group, which shows that you can realize this kind of long-range magneton transport using an easy axis phase of alpha iron oxide. It was quite surprising result because you can realize a micrometer size spin propagation using antiferromagnetic magnetons, and nobody would expect antiferromagnet can transport spins. So this was quite important result. So today we are using the same material, which is alpha iron oxide, but simply in a different phase, in the easy plane phase, that is at room temperature. We do the experiment at room temperature. So the reason that we are interested in the easy plane phase is, first of all, because it's easy plane. That means for any direction within this easy plane, it can be a thermal equilibrium, stable equilibrium position, which is different from easy axis case. If it's easy axis, you only have one single direction, single axis for the new vector to lie on when it's in equilibrium. So you cannot talk about switching. But when it's in the easy plane phase or in the biaxial anisotropy phase, you can talk about switching from one direction to the other direction. Another important reason is that for easy plane phase, there is this kind of weak ferromagnetism, which is well known. Well, basically, what it says is that in this easy plane phase, although it's antiferromagnetic, but there is a small misalignment between those two sublattices. So there is a canting angle that is generally smaller than 0.1 degrees, which is very tiny. That small canting angle gives rise to a finite magnetic moment. And then by utilizing this finite magnetic moment, we can use it as a leverage or handle to use external magnetic field to cause some magnetic dynamics. So that's the reason we think this weak ferromagnetic phase of alpha iron oxide can give us some advantages in realizing antiferromagnetic, in studying antiferromagnetic dynamics. Well, one natural question is why there is such a canting angle. So why there is a spontaneous symmetry breaking? Why it's not completely antiparallel with each other? Well, the answer is it's caused by DMI. So I think recently there are intensive interest in DMI, in studying DMI, because we know it causes chiral domain structures and it gives rise to topological structures like skernium. But actually the DMI was first studied and discovered when people try to understand this net moment inside alpha iron oxide. So there are very sophisticated DMI theories, which I'm not an expert on, but basically those DMI, in order to tell whether there can be a DMI or not, basically you need to rely on symmetry argument. So one rule says that, okay, if you have two spins, let's say here, S1 and S2, if those two spins, if the connection line of those two spins represent a rotational symmetry, a rotational axis for a certain n-fold symmetry, then basically the DMI D vector will be aligned along the connection direction between the two spins, S1 and S, the two atoms, S1 and S2. So for iron oxide, as you can see that S1 and S2, of course, come from iron atom. And then those open circles, 1, 2, and 3, represent oxygen. And you can tell this vertical line represents a threefold rotational symmetry, has a threefold rotational symmetry. So that's the reason why we can say, hey, there can be a DMI D vector along this vertical direction. After you have this finite DMI D vector, you can imagine when S1 and S2 are not completely collinear with each other, but instead form an angle, you can get a lower energy compared with they are purely collinear with each other. So that's the reason why there is a spontaneous symmetry breaking. So this DMI gave rise to a small canting angle, and it leads to a net magnetic moment, which is very small, which is only about 1/1000th of regular ferromagnet. Because we know for regular ferromagnet, the saturation magnetization is usually in the order of 1000 of EMU per cc. But for iron oxide, usually it's about 1 or 2 EMU per cc. So it's very small. So that ensures that this net magnetic moment will not completely dominate magnetic dynamics, so that you can still expect to get the magnetic dynamics that come from the Néel vector. Another thing is that this net moment and the Néel vector are orthogonal to each other. So that's basically you can easily separate their different contribution to magnetic dynamics as well as to some transport properties, as I will show later. And finally, another important property with this easy plane alpha oxide is that it has very weak in-plane anisotropy. So basically, you can use a magnetic field that is smaller than 0.1 Tesla to realize spin flop or to switch, to rotate the Néel vector direction, which is 1 or 2 orders magnitude smaller than regular antiferromagnet. Okay, so now we need to develop this material in our lab first. So the way that we grow this film is by sputtering. So first of all, we notice that this alpha iron oxide has very small lattice mismatch with sapphire aluminum oxide. So that means we can use aluminum oxide as a substrate for alpha iron oxide, which both of them have a hexagonal crystal structure. And from the growing 120 nanometer alpha iron oxide thin film XRD data, you can see that there is relatively narrow peak corresponding to the diffraction of this iron oxide. From rocking curve, which is the inset, you can also see that there is a relatively narrow line width, which reflects the fact that the thin plane of the iron oxide is perfectly aligned parallelly with the substrate surface. And also we can do the AFM study. As you can see, there is an atomic step. And also there is this kind of triangle shape, which suggests, which is consistent with the crystal structure of alpha iron oxide. Okay, after this structural characterization, we can start to look into the magnetic properties of iron oxide. Basically, we do a squid measurement at room temperature. But this measurement is actually non-trivial. The reason is here we are trying to measure a very small, very tiny saturation magnetization, very small moment. As I said, it's only about 1/1000th of a regular ferromagnet. So you can imagine you have to be very careful to separate the contribution from the magnetic from the substrate. So any diamagnetism or paramagnetism from substrate needs to be subtracted correctly. Also, if there is any contamination inside your lab, you will probably get very strange results. But after you carefully get rid of those contributions, you can get the MH curve for alpha iron oxide. As I said, the MS is about 1 to 2 EMU per cc, and then the porosity is below 1000 Erstat. So that means it's a very soft material within the EZ plane. Besides this kind of in-plane measurement, we can also measure the MH curve along the outer plane, along the hard axis direction. But in this case, as you can see, basically there is no effect So that means there is very large hard axis uncertainty. After the magnetic measurement, we can start to do some electrical measurement by making this kind of platinum alpha iron oxide bilayer structure. So we basically spatter 5 nanometer of platinum on top of iron oxide, and then pattern the device into this kind of Hobart structure. So we can measure the resistance either longitudinally or transversely. So we can get this kind of spin-Hall magnetoresistance effect. So the spin-Hall magnetoresistance effect, we can actually, from its shape or from its peak and valley location, actually we can tell whether it's dominated by the Néel vector or if it's dominated by the net magnetic moment. Let me make some explanation about SMR inside, spin-Hall magnetoresistance inside antiferromagnet. So when you have a bilayer structure of heavy metal and antiferromagnet insulator, you can think about the spin-Hall magnetoresistance this way. So basically, you will have a spin injection from heavy metal into antiferromagnet using through the spin-Hall effect. And if the injected spin is collinear with this Néel vector, then basically you will get minimum absorption of this spin, which will be reflected back. So that means that you will get the lowest resistance. But when this injected spin is perpendicular to the Néel vector direction, you get larger absorption of the injected spin, and then you get the highest resistance. Actually, this will be completely opposite to the case when this spin is absorbed or reflected by the net moment, because you will get a 90 degrees difference between those two cases. Then if you compare that picture with this observed spin-Hall magnetoresistance curve, you can tell that it's dominated by Néel vector instead of related to the net magnetic moment. Okay, so then from this sense, this alpha oxide is nothing different from a regular ferromagnet, antiferromagnet. You don't need to worry too much about the net moment. Another thing is, you can either measure the spin-Hall magnetoresistance in the longitudinal direction, or you can measure it in the transverse direction in the Hall geometry. The reason is, just like AMR effect, SMR can lead to a planar Hall effect, which is just a geometry effect. So in the following, we will focus on this planar Hall measurement. The reason is the signal to noise ratio usually is better in the Hall resistance measurement rather than the longitudinal measurement. And we found that for a field that is about 4,000 Ørsted, actually the SMR curve is largely separated. So that means 4,000 Ørsted is about very close to the separation field. So then you can use a effective single domain picture where all of the magnetic Néel vector or all of the magnetic moment direction are aligned by this external field. So you can use a very simple domain picture without worrying about domain walls or other complicated structures. Okay, so after we develop this material system, we start to try to correlate the current-induced effect inside this platinum alpha oxide bilayer structure with some magnetic dynamics using field as a ruler, as a caliper. Well, basically, the first experiment that we try to do is to realize this kind of current-induced switching. Just try to follow what has been done earlier in other material systems. As you know, if you want to realize a Néel vector switching, the most popular device geometry is this kind of 8-terminal device geometry, where you can apply current in two orthogonal directions to flip the to rotate the Néel vector between two orthogonal directions. And then in order to read out the Hall resistance, you have to read it in a 45 degrees direction. That's the reason why you need an 8-terminal device. So in our measurement, we've basically used the 4-terminal geometry instead, which follows some following some previous work. The reason that you can also realize this kind of Néel vector switching in a 4-terminal device is because you can potentially apply current along two orthogonal directions at the same time. So basically, you use the same current source, but you connect to two channels at the same time. And then the superposed current will be along the 45 degrees. And then you can measure the Hall resistance in the regular geometry, which also realizes this kind of 45 degrees current flow. So this is approach that we use, mostly to save some fabrication efforts. So basically, the first to zeroth order, what we found is that we do find this kind of sawtooth-like switching, where the Hall resistance toggles between some high resistance and low resistance states. So after seeing this, and after the first data points, we found that we thought that, okay, this probably reflects the Néel vector switching in this material system, and we were quite happy about it. And then following that work, we start to try to see if we can use magnetic field to get some further information about this kind of switching. As I said, since alpha oxide can be relatively easily controlled by the external field, then we start to compare the two cases where we have pure current pulse induced switching without any magnetic field, with the case where we have the current pulse induced switching under a constant external field, which is the bottom panel. To our surprise, we found that actually, no matter whether we apply this external field or not, the switching shape is roughly the same. We get a similar sawtooth-like switching behavior. And this external field actually plays very little role, although the magnitude is not small, because we know from our previous magnetic measurement, we know 2000 Ørsted is already larger than the corrosive field or larger than the Schmidt-Floch field, which in principle should be strong enough to suppress most of the Néel vector switching. But surprisingly, the field does not play a significant role. So this casts some doubt on the magnetic origin of this kind of observed resistance switching. And following that, we also did another experiment to try to see if this observed switching is really related to Field's effect. So the way that we do it is basically we first use current pulse to switch the magnetic ordering. And then after the switching, we use magnetic field to try to switch it back or try to measure the Schmidt-Floch magnetoresistance. So in theory, if the switching, current-induced switching is due to magnetic switching, then when it goes from valley to a peak position, then we can probably utilize field to switch it back. And then we can get a relative change in the peak or valley position as told from the SMR curve. Again, what we found is that this kind of current-induced switching is completely irrelevant, not related to the field-induced Schmidt-Floch magnetoresistance change. So there is no relative change between the peak and the valley position after the current pulse switching. But instead, the current effect is simply shift the overall resistance of the Schmidt-Floch magnetoresistance curve. And under some large current, for example, in this 45 milliampere case, this overall shift can be even much larger than the total magnitude of Schmidt-Floch magnetoresistance caused by field. So basically, this experiment suggests that the observed switching is likely not due to a magnetic switching in this system, but instead it's purely some artifact due to some electrical breakdown or some thermal effect. So we looked it up and we found that, okay, the current that we use in order to realize this resistive switching is in the order of 10 to the 7th to 10 to the 8th ampere per centimeter square, which is already in the range of causing electrical breakdown for platinum. So actually, if we look up in literatures, we will find that there are studies in trying to study the electromigration effect in pure platinum field. And you can see that, okay, under a current along different directions, you can induce some a certain island to cause this kind of electromigration, or you can recover it if you simply change the current direction. So basically now that our tendency is to believe that this kind of observed current-induced switching in this iron oxide system is probably due to the electrical breakdown or electromigration inside platinum. So we found that at the same time, or quickly after our observation, there are also other reports showing similar effects. One work by the Johns Hopkins group, which studied the platinum nickel oxide bilayer structure. And also there is a paper from Ohio State, Professor Young's group, where they showed that using the same alpha oxide platinum, where they also showed that there can be non-magnetic switching And on top of non-magnetic switching, and there is also a certain window where you can get this real magnetic induced switching in this paper. So I will also talk about real magnetic effect later on. And also there is also the work from Professor Geoffrey Beach's group, which also studied platinum nickel oxide. Okay, another thing that I should point out is that the four-terminal geometry that we utilize is probably makes things even worse. The reason is in four-terminal device, basically when we try to get this kind of 45 degrees current application, we have to apply current in two directions, and then the current are actually heavily crowded in those two corners. And then if you calculate the temperature, and you will find that the temperature will increase by more than 100 degrees K. So that can potentially cause a big, that's probably the weakest point, the hot spot where the electron migration can happen. Okay, so after this, we were quite disappointed because we thought, okay, we did not observe any magnetic, real magnetic signal. So the next question is, how can we possibly quantify the current-induced effect? Well, now again, we try to learn something. We try to borrow some knowledge from our ferromagnetic study. And we know in the recent, for example, the recent example on quantify the current-induced effect in ferromagnet might be the spin-orbit torque effect. In spin-orbit torque effect, we know in order to quantify its magnitude, there are a few things that we should keep in mind. First of all, it's better to keep the current low. So it's better not to study the effect in the switching regime, but instead use a much smaller current. Because when you have a much smaller current, then you can largely avoid those nonlinear effects like electron migration effect. So lower current will definitely be helpful. And secondly, we utilize the current-induced tilting versus field-induced tilting to calibrate the spin-orbit torque. So basically, you can use a small current to tilt magnetic moment slightly away from its equilibrium position, and then compare it with the corresponding effect from external field. Actually, that's also the underlying principle behind the second harmonic measurement. There is the same idea. You tilt the magnetic moment slightly using spin-orbit torque and compare it with field-induced tilting. Another thing is, it's probably better to work in the single domain coherent rotation regime instead of multi-domain regime in order to quantify the current-induced effect. The reason is, if it's a multi-domain regime, then you have to consider the detailed mechanism for domain motion or for domain nucleation. And that makes things quite complicated. But in a single domain or field-induced single domain case, at least things are you can get things analyzed very easily. Okay, so this is basically the rough idea. We still utilize this kind of Hobart structure, and then we apply an external field. And this external field, of course, will first of all try to align the nu vector or try to align the magnetic moment along a certain direction. And then we apply this external current. And this external current, if there is any effect, it will try to tilt this nu vector within this easy plane. And then by quantifying that tilting angle, we can potentially get some knowledge about how large or how small this current-induced effect is. And also, in order to do this experiment, we use DC current instead of pulse current. The reason is, as we learned from earlier experiment, that pulse current usually can cause some vertical shift, which will complicate things. So we use a DC current so that it does not cause this kind of resistive switching. Okay, so basically this is the results that we obtained from this kind of current-induced tilting experiment. We first applied the current in the horizontally in the film plane, and then we rotate the external field from 0 degrees to 360 degrees and get the SMR signal. So we know that basically for each corresponding point on the SMR curve, it corresponds to a certain magnetic moment angle. And then when we increase or we vary the current from 2 milliampere to 20 milliampere, we found that the spin-Hall magnetoresistance curve, its shape does change. So actually 2 milliampere corresponds to a very low current density. We can basically neglect the current-induced effect and treat it as baseline. And then for 20 milliampere, we found that if we compare those two cases, we found that actually the peak position of the spin-Hall magnetoresistance shifted to the first peak position shifted to the lower angle orientation. What does this mean? This means we know for the spin-Hall magnetoresistance to show a peak, actually you need to align the magnetic moment or align the new vector along the 45 degrees direction. So now under the current, we need a field angle that is smaller than 45 degrees in order to achieve this peak. So that means this new vector actually try to align, this current try to align the new vector parallel with its orientation. So basically that's what this trend tells us. The new vector's influence is to try to tilt the new vector more parallel with its flowing direction. Of course, we can also change the current flow direction from horizontal to vertical, and this is what we get. We found that when we change the current flow direction to vertical, actually the first valley position goes to a higher angle region, which is also consistent with the picture that the current tend to align the new vector parallel with its the current flow direction. The fact that when we change the current from horizontal to vertical, the spin-Hall magnetoresistance curve changes oppositely, also suggests that this is not just a simple trivial thermal effect, current effect, but instead it does reflect some underlying magnetic ordering change or magnetic ordering tilting. Now the question is, what causes this magnetic moment tilting? What's the exact mechanism? Of course, the first consideration is about spin-orbit torque. Can it be from the spin-orbit torque? Here we need to be give it some more careful consideration, because it's not that straightforward to figure out how a spin-orbit torque can tilt the magnetic moment within the easy plane. We can consider this kind of geometry. Basically, you have Platinum, which injects spin into an antiferromagnetic insulator, which has easy plane geometry. And we know this injected spin has the largest effect when it's orthogonal to the new vector direction. If the new vector is parallel with the injected spin, basically there is not much effect. When it's orthogonal to the new vector direction, to the first order, we know the spin-orbit torque will try to tilt new vector out of plane. The reason is, no matter which sublattice you consider, you can write out the torque expression. The spin torque is m cross sigma cross m. And this sigma cross m usually is described by effective damping-like torque. And then you can imagine that this damping-like torque is either out of plane for one sublattice or below the plane for the other sublattice. So basically, it will try to tilt the new vector out of plane. And as soon as this new vector is tilted out of plane, it will experience the effective field from the hard axis anisotropy. And that hard axis anisotropy is along an anisotropy field is along the z-axis. And then you will get this kind of the anisotropy field induced torque, which try to tilt the magnetic moment within the plane. So that can give you a tilting within the easy plane. So basically, in principle, in this single domain picture, spin-orbit torque can induce this new vector tilting within the easy plane through this second order effect. However, if you do a more careful study, for example, if you numerically solve this LRG equation, this coupled LRG equation for those two sublattices, what you will find is that the new vector actually will be tilted more perpendicular to the current direction rather than more parallel with the current direction, which is opposite to what we observed previously, which is tilts the new vector more parallel with the current direction. Another thing is we also found that magnitude is probably off by quite a lot. It's by more than one order magnitude. So regular spin-orbit torque is not enough to cause the tilting of this new vector that we observe in real experiment. Okay, so now the question is, what is this effect? Okay, so in order to get a more quantitative analysis, instead of just tracking the tilting, instead of just tracking the change of the peak or valley position, we start to utilize the energy picture, because for each data point on the SMR curve, as I mentioned, each data point can be related to a certain magnetic moment angle. If you know this magnetic moment angle, and also if you know what the applied current is, then you can basically calculate the magnetic energy associated with this structure. So basically what we found is that we get a magnetic energy change between the lowest applied current and the highest applied current. First of all, you observe that this energy have a 180 degrees dependence on the angle, applied field angle, no matter what current you apply. This suggests there is a uniaxial anisotropy energy. And even under the lowest applied current, we found that there is a finite, or actually quite large, anisotropy energy. Actually, this comes from the intrinsic uniaxial anisotropy within the EZ plane. And I said, although it's an EZ plane, but there can be some high order anisotropy within the EZ plane. So actually it happens that there is a uniaxial anisotropy within the C plane of alpha iron oxide. And we found that the current influence is that as we increase the current, actually this uniaxial anisotropy changes. And then finally, when we apply a large enough current, this uniaxial anisotropy energy even changes sign. So that means originally the 0 degrees and 180 degrees is the EZ axis within the EZ plane. And now under 20 milliampere, actually now the 90 degrees and 270 degrees become the EZ axis within the EZ plane. So basically, the current effect is change this uniaxial anisotropy within this EZ plane. Of course, we can also compare the results under a positive current and a negative current. We found that to the 0th order, those two are quite comparable to each other. So the flipping the current direction does not change things much. It's in both cases, we change the uniaxial anisotropy from positive to negative. But there is a tiny difference. If you keep an eye, if you monitor the change in the 270 degrees energy and also the 90 degrees magnetic energy, you will find that actually there is a slight asymmetry between those two cases, and those asymmetry is different between the positive and negative current case. Okay, so basically to summarize, what we found here is that the current effect can have two components. The first component reflects the fact that uniaxial anisotropy goes from positive to negative. So that is basically a current-induced uniaxial anisotropy energy change. And the other one is basically there is a asymmetry between 90 degrees and 270 degrees. Basically, this kind of symmetry basically reminds us about Zeeman energy, because Zeeman energy has a 180 degrees difference. So basically, this can be described as a unidirectional Zeeman energy term. So now in the following, we will focus on those two energy terms, even part and odd part. First of all, the dominant part is even part. We can do a series studies. First of all, we can vary the applied current and then see how does this even part of the magnetic energy change. We found, well, simply it followed a G-square term. So basically a G-square behavior. So basically the energy changes proportional to G-square, current density square. Well, this first of all reminds us about some thermal effect. And secondly, what we found is that actually there is also a device size dependence. Those different colors, red, blue, purple, yellow, actually those correspond to different sample weights. So we made a device channel with different weights. We found that there is also a weight dependence. Well, this is, again, not consistent with a spin torque picture, because in spin torque, it should only be dependent on the current density. It should not be a function of the sample size, sample weights. And finally, we can also compare two different samples. One is 10 nanometer iron oxide, and the other is 5 nanometer alpha iron oxide, which represented by different symbols, square versus star. As you can see, when we use two different thicknesses of alpha iron oxide, actually their behavior are quite consistent with each other. There is no thickness dependent. But for spin orbit torque, we know because it's an interfacial effect, so it has to depend on the thickness, or inversely dependent on the thickness. So basically, these few aspects suggest to us, again, this is not a spin torque effect. What we observe in this system is not a spin torque effect, but instead is a thermal effect. But how can a thermal effect contribute to the magnetic part of the energy? So, or if it's just a simple trivial thermal heating, and then it just weakens the anisotropy, then you should not expect a sign reversal in the anisotropy energy. So basically, it needs some more sophisticated mechanism. other than a simple heating-induced weakening of anisotropy. So what we find is one mechanism that can be potentially responsible for this effect is due to the thermally induced magnetoelastic effect. Well, let me explain step by step what this means. Well, the thermally induced magnetoelastic effect, first of all, from the zero heating, you can get a thermal expansion of the lattice. And then this expansion of the lattice will be highly anisotropic. The reason is whenever we do this kind of current-induced switching measurement, we have to make a long wire. So it is much longer in one direction than in the other direction. And correspondingly, the stress in the current flowing direction will be much larger than the stress in the transverse direction. So now you have a net stress from the substrate lattice. And then if your magnetic material has some magnetoelastic effect or magnetostrictive coefficient, then that can cause an anisotropy change. Particularly for alpha oxide, we know it has a sizable magnetostrictive coefficient. And then that can cause a uniaxial magnetic anisotropy change. We found that if you utilize the literature reported alpha oxide magnetostrictive coefficient, both the sign and the magnitude are consistent with our experimental observation. So basically, you can model the thermal effect and and the stress effect very well using some software package like Console. And then we found that quantitatively, you can explain all of the magnetic energy change that we observed with different size of samples, with different thickness of samples. So we can make the conclusion that the even part of the energy change is due to a thermal magnetoelastic effect. And then next, what about the odd part of energy change? As we said, it's more like a Zeeman energy because 0 degrees is different from 180 degrees. Well, the Zeeman energy, there are two possibilities. One is it's a real Zeeman energy because there is current-induced Earth-state field. The other possibility is that this comes from some field-like torque of spin-orbit interaction. So we try to answer this question by doing, again, compare different samples with different thicknesses and also samples with different sizes. What we found is that, first of all, it does not have any size dependence. That means it's not a thermal effect. So it is from a Earth-state field or spin field-like torque effect. And secondly, we found that actually when we double the thickness of our oxide, actually the torque, this damping-like torque or this Zeeman energy term reduces by 1/2. So if you compare the left versus right panel, that's 10 nanometer versus 5 nanometer. You can see that slope reduces by roughly a factor 2. So that means this is reflect a field-like torque, just similar to conventional ferromagnet. Okay, now let's quickly summarize what I showed today. Well, basically, first of all, I showed that when we studied the current-induced switching in platinum alpha oxide bilayer structure, we found that in this system, things can be communicated with extra effects like electromigration and thermal magnetoelastic effect. And particularly, when we use this kind of four-terminal device geometry, things become even worse. So I think we have to be careful to enlarge the window where you get the magnetic switching, try to minimize or push the electromigration effect further away. And also another thing is, I think we show that alpha oxide in its easy plane phase, it can be potentially a good candidate that can bridge AFM to FM because we can connect the antiferromagnetic phenomena to some well-known physics or some useful tool sets that we have developed for ferromagnetic study. And then we, by comparing the current-induced effect with a field-induced, using a field as a standard, we can get a quantitative measurement on this magnetic dynamics in antiferromagnet. And then finally, I guess the question is, can we possibly extend to other antiferromagnet for those even without a weak ferromagnetism? I think the answer might be yes, so long as we can keep a very weak anisotropy within the easy plane. In principle, we can also realize a small spin flop field and then rotate new vector within the easy plane. Okay, finally, let me introduce the people who did the real experimental work. This work is leading by the PhD student, Pengxiang Jiang, and then in collaboration with Joe Finley and Takia Safi. So basically, that's all for my today's talk. Thank you very much for your attention.
Thank you very much for the nice talk. For the audiences, we can send a round of virtual applause by clicking the reactions button at the bottom of the Zoom screens. So if you have questions, please use the raise hand options. You can click the participants at the bottom of the Zoom screen and then click raise hand at the bottom of the pop-up panel. And for folks watching on Twitch, if you want to ask a question, please go to Microsoft Teams under the channel with Luqiao's name, and you can type in the questions there, and I will read it for you. The first question will be asked by Professor Yan Chen. Please go ahead, unmute yourself and ask a question.
Hey, Luqiao. Thanks very much for your very nice talk. So I have two questions. One is about the early part. So you mentioned that the SMR signal is related to the Néel vector n, but not the small moment m.
Yes.
So I was wondering how did people know this? I think you went a little bit fast.
Yeah. So let me explain again. So basically, well, the mechanism for SMR is that when you have an injected spin parallel with the moment or parallel with the Néel vector direction, you get absorption.
Yes.
So for antiferromagnet, for ferromagnet is when sigma is parallel with m, then you get a largest absorption. So remember the Néel vector is orthogonal to the net moment.
Right.
If it absorbs by the net moment, then when the Néel vector is parallel with the current, you get the largest absorption. When it's absorbed by the Néel vector, then it's when the current, when the Néel vector perpendicular to the current, you get the largest absorption. So those are opposite to each other. So that's the reason why you can tell it apart.
Oh, I see. Okay, so it's just so you can tell it from the position of the peak and the zeros from the. Okay, I see. So then what about, okay, so in the same setup, if you look at the data from the second harmonic, which is the thermal effect in this geometry, then presumably it is the small m that matters for the second harmonic.
Sorry, I didn't think through about second harmonic. We didn't measure second harmonic. The reason is we try to use DC measurement.
Oh, it's pure DC measurements.
Yeah, so because AC measurement will, I mean, many things are buried underneath, so it's less transparent. So we try to use a DC measurement. So all of the measurement are DC measurement.
Oh, I see. Okay.
Yes.
Okay, thanks very much.
Yeah.
Professor Hua Chen, you're next. Please unmute and ask the question.
Thanks, Jim. Thanks, Luqiao, for the very nice talk.
Thanks.
I have a few questions. The first is, since hematite is a weak ferromagnet, it from symmetry point of view, it's pretty much can be understood as a ferromagnet, except for the very strong anisotropy, easy plane anisotropy. In the current setup, it seems that it's hard to make use of the damping-like torque because it tries to rotate it out of the easy plane.
Yes.
So you considered to grow the sample with the easy plane perpendicular to the whole bar plane.
That's a good question. So thank you for pointing this out. So yes, so basically the spin-orbit torque will be more efficient if the injected spin is perpendicular to the easy plane. That requires you to grow the film in a different orientation. But that's doable. But in principle, that's doable. But there could be some technical difficulties. The reason is when you grow it along some axis other than the c-axis, other things can contribute. So yeah.
Yeah, of course. But a appealing point is there might be an enormous Hall effect that can let you directly measure the direction of the weak magnetization if you grow it. Yeah. Another question is for the field-like torque that you finally determined.
Yes.
You try to convert the size of the torque to an effective magnetic field.
Yeah, so I think we have the number in the paper. So although I don't have the number in my head, I think it's comparable to regular ferromagnet. So it's not that.
Okay, all right, thank you.
Okay. Wei Yuan, please go ahead with your question. Wei,
okay,
are you there?
can hear me?
Yeah.
So you hear me?
Yes.
Yeah. In the first you talk about the Mori transition temperature is around 260 Kelvin, but
Yes.
in your measurement you use the thin film. I don't know if the Mori transition is significantly different.
Yes. So thanks for the question. So actually, the reality is the Mori transition will be significantly influenced by the thin film geometry. So in thin film case, because there is very strong strain from the lattice, from the substrate to the alpha oxide. So actually, this Mori transition can be greatly suppressed. So even if you look at previous literatures, you will find that the Mori transition can even be absent. So that means there might not be Mori transition. Even down to the lowest temperature, you still get an easy plane phase. So we verify that. Yes.
Okay, good. Thank you.
Thank you. Do you have other question? I just want to ask a quick question for the iron oxide. Have you tried measuring the spin seeback effect by growing platinum on top of that?
No. No, we didn't.
Okay. I may ask for some samples actually when this is over.
Okay, sure.
All right. Is there any other question? And I don't see any question from Twitch either, from Teams. So if there's no other question, let's thank the speaker again.